Welcome to my presentation, Water-soluble organic fluorophores with powerful electrochemical and photophysical properties, which is part of the virtual ACS Spring Meeting 2020. In the next couple of minutes, I will share with you the key results obtained during my PhD studies in the group of Professor Christoph at the University of Basel. Small molecule organic fluorophores are extremely fascinating and simply beautiful to look at. Additionally, they're also very helpful in visualizing and supporting our understanding of the complex interplay of biomolecules. This is a fluorescence microscopy image with three distinct fluorophores, fluorescein, rhodamine, and dapi. Century-long development led from these simple fluoresceins and rhodamines to quite complexly substituted organic fluorophores with distinct dye properties and diverse colors. This includes unsymmetrically substituted fluorophores such as Atto-647, which is present as a racemate due to isomerism that occurs from the restricted rotation about the single bond. Interestingly, the distinct interactions of the two enantiomers in a biological environment are still unexplored today. Also, current dye syntheses still rely on archetypical biocondensation and Burnson-type reactions. These often require high reaction temperatures, an additional oxidation step, or highly reactive reagents that limit the desired dye diversity. Also, the more modern heteroantron addition of organometallic reagents would require multiple steps to readjust and change the substitution pattern on the heterocyclic moiety. Therefore, a transformation of stable, readily available starting materials accessing distinct fluorophores in a modular fashion under mild reaction conditions would be highly desirable. Aside from bioimaging, small molecule organic fluorophores are also becoming increasingly interesting for photocatalysis. The use of visible light and the photocatalyst enables the investigation of new reactions, which are not accessible under typical thermal conditions. Similar to fluorophores in bioimaging, also in photocatalysis, the excited state lifetimes, the quantum yield of both fluorescence and intersystem crossing, but also the molar absorption coefficient and absorption and emission wavelength are of great importance. Although in this short presentation, I would like to focus, for the most part, only on the excited and ground state redox potential, as these are the most fundamental key to understanding the reactivities. So when a photocatalyst is irradiated by light, it can absorb energy from a photon and it excites an electron into a higher energy state. This provides an increased driving force for single electron transfer. Depending on the nature of the photocatalyst and its surroundings, it can either act as an excited state reductant, where an electron is released from the photocatalyst to the substrate, or an oxidant, or in another scenario, an electron is taken up from the substrate, or the reductant, and where the photocatalyst then acts as an excited state oxidant. Subsequently, thermal re-reduction or re-oxidation then gives back the initial photocatalyst. This enables further reactions and eventually product formation. It is, however, very important that in both steps, the half reaction potential of the photocatalyst matches the half reaction potential of the substrate to prevent side reactions or unproductive reactions from occurring. Therefore, we require access to various photocatalysts with quite nuanced redox properties. Today, most commonly used photocatalysts are these polybipyridyl-based transition metal complexes. Their excited state reduction potential, shown here along this arrow, can be modulated by changing the ligand scaffold. This is not really possible for organic fluorophores, but recently Lysevich and DiRocco introduced electron-rich methoxy groups to lower the excited state reduction potential of the highly oxidative Fukutsumi catalyst. However, as you can see, there is still room for improvement as these organophotocatalysts do not come close to the powerful yet expensive transition metal complexes. Furthermore, current advances in photocatalysis with exciting applications in biology would benefit from the increased water solubility of these acridinium derivatives. Similar to fluorophores used for imaging, we could also benefit here from a modular dye assembly strategy that accesses diverse substitution patterns with distinct redox properties over a broader range. So in a prototypical heterocyclic fluorophore, we would like to modulate 5 parts. This would be the heteroatom, in some cases substitution on the heteroatom, but also substituents on the A, B, and C ring. Arguably, in organic synthesis, we have good accessibility to various substituted arenes and coupling reactions to functionalize arenes and bridge the A and C ring via a heteroatom. However, we require improved methods for the formation of the B ring under mild reaction conditions and enable various and diverse substitution. Metallation would allow for an activation for a nucleophilic addition to carboxylic acid esters. And esters are ubiquitous and stable reagents, allowing for great diversity at this position. And by choosing different metallation strategies, the substitution pattern can be varied. So by starting from dibromides, we could aim for a double halogen metal exchange. But in the presence of directing groups, such as these methoxys, this could enable a double directed ortho-Metalation. Or of course, the combination of both strategies would allow for even further heterocyclic fluorophore derivatives after the addition to esters. So with these strategies, we aimed at investigating a modular synthesis of Xanthylium, SAR, and Acridinium fluorophores. Our starting point was built by the direct ester to arene transformation, where we used 1,5 bifunctional organometallic reagents to allow for a double nucleophilic addition on esters to form cyclohexadienolate intermediates that are prone to undergo a spontaneous 1,4 elimination to form substituted benzenes, anthracenes, and different linear and nonlinear acenes. Together with my colleague Achim Link, we found a high-yielding method which could form privileged scaffolds without transition metals, yet use highly available starting materials under mild reaction conditions with a broad substrate scope. This rendered a reaction that later even high school students were able to successfully perform. This motivated us to introduce a heteroatom into the 1,5 bifunctional organometallic reagent and investigate the formation of heterocyclic fluorophores. However, the 1,4 elimination will no longer be possible with a heteroatom in the backbone, so we aimed for an acid-promoted dehydration instead. The desired 1,5 bifunctional organometallic reagent to transform esters into xanthylium salts was synthesized in 3 steps. This involved the copper-catalyzed Ullmann coupling that established the bi-aryl ether bridge, followed by a double bromination that proceeded with very high Ricci selectivity and a double halogen metal exchange with magnesium. The reagent was directly added to methyl benzoate. After confirming the double addition and formation of the intermediary alkoxide, treatment with hydrobromic acid induced the dehydration. This is one of the most beautiful reactions I've ever seen, forming the rosamine bromide salt in its very intensive bright colors. And it makes especially column chromatography very enjoyable, as you can see here irradiated under 366 nanometer UV light. So aside from methyl benzoate, we also transformed electron-rich, electron-poor, and sterically hindered, but also alkyl and alkenyl esters in good yield. This encouraged us to further investigate modern silicon-containing SIR dyes, which are especially useful in fluorescence microscopy due to their far-red emission and good water solubility. As the pioneering synthesis is step-intensive and of rather low robustness, we aim to improve the accessibility of those dyes. A halogen metal exchange and addition to the dimethyl dichlorosilane established the silicon bridge, followed by a beautifully Ricci selective double bromination that allowed the synthesis of the precursor in multigram scale. A double halogen metal exchange then gave access to the reagent, which was stable for at least 60 days at room temperature on the argon. But the addition of this reagent to methyl benzene still allowed for another beautiful reaction. After acidic workup and purification, it led to a nicely blue-colored Si-rosamine. We investigated also a broad scope, but especially interesting is that with this assembly strategy, we can directly introduce various functional groups such as bromides or esters that allow bioconjugation and photofunctionalization without the need of any additional steps or protecting groups. The protic aniline we installed by using an additional equivalent of the reagent and could confirm the structure by X-ray crystallography. The method proved to be highly robust, allowing gram-scale synthesis of this derivative. Interestingly, this aniline derivative has a very small fluorescence quantum yield due to an intermolecular photo-induced electron transfer, which we could prevent by removing the electron density and install electron withdrawing groups, either via A-site formation or a simple acetylation. This allowed for a 100-fold increase in fluorescence quantum yield, which makes this fluorescence enhancement strategy potentially useful for microscopy or bioassays. To apply the same fluorophore assembly strategy to acridinium salts, we coupled an aniline and iodoarene scaffold with a Buchwald-Hartwig amination with the bromides already in place, followed by the methylation and the halogen metal exchange. For photocatalysts, the two ortho-methyl substituents on a mesotyl moiety are indispensable as they shield the part of the acridinium from nucleophilic and radical attack. Therefore, it was particularly gratifying that we could access the highly sterically hindered mesotyl derivative in 74% yield. Changing now from double halogen metal exchange to double directed ortho-Metalation by simply using N-Buli allowed access to novel dimethoxy substituted acridinium salts, both N-methylated or N-phenylated. A workup with ammonium chloride instead of hydrobromic acid afforded access to the acridinol intermediate, but also the reaction with various esters could be investigated. We further introduced 2 or 1 dimethyl amino groups where we gained access to non-symmetrically substituted acridinium salts. This allowed the formation of configurationally stable atrop isomers that we separated by HPLC equipped with a chiral stationary phase, allowing future application as enantiomerically enriched molecular probes. With the mixed methylation strategy now, we obtained specifically unsymmetrically substituted acridinium salts, methoxydimethylamino or just one methoxy group, or with a uniquely positioned dimethylamino group. We also examined the formation of xylyl instead of mesotyl derivative, as this additional methyl group on the mesotyl is often prone to undergo side reactions. Now let's go back to the beginning and look again at the excited state reduction potential scale. Could we actually tune the dye properties by introducing this modular approach for the synthesis of diversely substituted heterocyclic fluorophores? The day we examined the properties of the diamino substituted acridinium salt for the first time was particularly exciting, because introducing dimethylamino groups influenced the dye properties dramatically. It showed a highly attenuated excited state reduction potential compared to previously reported acridinium salts, and the ground state reduction potential was enhanced, matching the reduction properties of this frequently used heteroleptic iridium complex fairly well. Introducing 1,8 dimethoxy groups accessed further diversity for rather stronger photooxidants, whereas the amino substituted derivatives showed again more attenuated excited state reduction potentials. The mixed methylation strategy then allowed modification over a broad range, accessing stronger and weaker organophotooxidants. One organophotocatalyst in particular came close to both the excited and ground state reduction potentials of the tris bipyrrocine ruthenium catalyst. Nowadays, a lot of research groups develop and investigate very beautiful photocatalytic reactions by using the currently available catalysts. Our exciting results now pose the question if we could replace the expensive transition metal-based photocatalysts. And one of these examples is the groundbreaking Photoredox nickel dual catalytic decarboxylative coupling described by Doyle and Macmillan, using this heteroleptic iridium photocatalyst that allows very efficient transformations. Both the unsubstituted and tetramethoxy substituted acridinium salt fail in this transformation, presumably due to the mismatching excited state and ground state reduction potentials. However, the newly accessed diamino substituted acridinium salt that matches the reduction potentials allows catalysis and coupling product in 86% yield. In collaboration with Christoph Kerzig and Professor Oliver Wenger, we examined the properties of the diaminoacridinium photocatalyst in more detail. The comparative DFT calculation of the Fukutsumi catalyst revealed fundamentally different HOMO-LUMO transitions. The introduction of dimethyl amino groups evidently causes a change from the highly reactive charge transfer character of the Fukutsumi catalyst to a less energetic pi-pi star character, seemingly more suited for complex multi-component dual catalysis. The unique properties of the diaminoacridinium catalyst were further underlined when we compared its reactivity to a large number of routinely used fluorophores and organic photocatalysts. Exclusively, the diaminoacridinium photocatalyst led selectively to the desired CC coupling product. In contrast, for example, eosine-Y led via a diverging triplet-triplet energy transfer pathway selectively to the O-aryl ester. The same iridium catalyst used for the decarboxylative CC coupling could also successfully be replaced in a decarboxylative fluorination. The diaminoacridinium photocatalyst withstands effectively possible catalyst degradation from the strongly electrophilic fluorinating reagent SelectFluor. In another example, Yoon and co-workers investigated an oxidative 3+2 cycloaddition to form dihydrobenzofurenes by using this tris-bipyrrocine ruthenium catalyst. For this reaction, the diaminoacridinium photocatalyst was less suited, but out of the mixed metallation series, we found a useful organophotocatalyst that allows for effective product formation. With this, I would like to conclude my talk. I hope I was able to convince you that the formation of 1,5-bifunctional organometallic reagents improves the diversity of currently accessible heterocyclic fluorophores by using the high availability and stability of esters, allowing for milder assembly than ever before. Additionally, directed ortho-Metalation and mixed metallation strategies can readily be applied to modulate the substituents on the heterocyclic fluorophores, shown here with the focus to create acridinium dyes with diverse photophysical and electrochemical properties that are capable to be used as organophotocatalysts that can replace expensive and rare transition metal-based fluorophores. With the help of Solvias, some of these powerful diaminoacridinium photocatalysts will soon be available through STREM chemicals, and I hope to see many new applications and reactions evolving out of this. First and foremost, I would like to thank my PhD advisor, Professor Christoph Spar, for his support and for letting me tackle such contemporary projects. I'm particularly grateful to the collaboration and countless discussion with Professor Oliver Wenger, Christoph Kerzig, Achim Link, and Buthaina Silat. I'm also thankful to Solvias for supporting our endeavor to commercialize our photocatalysts. And I thank all the members of the Spar Research Group for their support and friendship. I appreciated the invaluable support of Daniel Heusinger and Thomas Müntener in NMR spectroscopy, and Markus Neuburger in X-ray crystallography. Last but not least, I thank the University of Basel for funding me during my PhD studies, and the Swiss National Science Foundation for an early postdoc mobility fellowship that allows me to stay here in the Trauner Research Group at NYU. Thank you for your attention, and please reach out to us if you have any questions or comments. You can find our contact information either on the last slide of the presentation or the last page of the audio transcript. Thank you very much.